Good morning. This is the first seminar in MATC Spring 2014 webinar series. We are really excited to have Dr. Chris Schwarz from MATC to be presenting on towards autonomous vehicles. Dr. Schwarz received his BS degree in electrical engineering from University of Illinois in 1990. He has received PhD degree in electrical engineering from University of Iowa in 1998, and he has worked as a research engineer at National Advanced Driving Simulator since 1998. This seminar is also closely related to a recent MATC project which Dr. Schwarz was working on, and a final report was submitted in 2013. And I'd like to hand it over to Dr. Schwarz to start his presentation. Thank you.
Hi, good morning. Just another note on the audio, you are kind of soft there, so maybe you just need to speak up when you're doing the questions later. That would be great. So yeah, thank you all for coming. Was very excited to do this project, and I'm very excited to share the results from it. The title of the report and of the presentation is Towards Autonomous Vehicles. And I just want to start with some acknowledgements. As was said, this was a project for the Mid-America Transportation Center. It was a one-year project to survey the field, do a literature survey, and write a report. My co-PI was Professor Geb Thomas in the Department of Mechanical Industrial Engineering. And over the course of the year, we had 4 undergraduate students who were able to help me out doing reading papers and developing some scenarios, and they were all really great. So the work products, there are a couple that you can get to. The first is the final report. It's on the MATC website at UNL. The second is the body of research. The papers are all collected in a Zotero group, and that's a public group. You can all go and actually grab any or all of the papers that we collected, and that's available at zotero.org. So I will refer you to those for all the references that were used, because I don't include a lot of the references in the slides. So autonomous vehicles are all the hype right now. You may not see them on the road a lot or at all, but it's hard to not see reports and news stories about them, magazine articles. So there's a lot of excitement, and it seems somewhat inevitable that they'll be coming our way at some point in the future. What I'd like to do with this talk is cover a little bit of the history, a little bit of the current state of the art, and the different elements of autonomous vehicles. Then talk about some of the challenges that they face, and a little bit of discussion on a couple of issues that I pulled from our research, and then we'll have some time for Q&A. The terminology, automation, autonomous, automated, semi-autonomous, there are a lot of terms. The government now prefers automated vehicles because it captures all of the different levels in between fully autonomous and fully manual. I'm not going to be strict in my use of the terminology. I'll use autonomous. I'll use automated sometimes. And of course, it's impossible for me to present at a level that will make everyone happy. I feel that this is kind of an intermediate presentation, not really for complete novices, but those of you who may be, very familiar with the field might think it's a little too simplistic or summary. So sorry if I don't hit everyone's sweet spot, but I hope it'll be interesting nevertheless. So what's the motivation for autonomous vehicles? There are a lot of visions for the field. One of the primary ones is safety. There's still, over 30,000 people who are killed every year, and over 90% of those are due to driver error. And beyond fatalities, there are many more injuries and lots of property damage as well. So the vision for autonomous vehicles is a crashless society. If you can eliminate all of the crashes due to driver error, then that's going to be a vast improvement and save lives. So the second area would be the area of mobility. One of the things that autonomous vehicles can provide for us is the ability to put a lot more cars on existing roads and then we would not have to keep adding to the infrastructure, adding more lanes, adding more roads. So this will require some fairly high market penetration, for the technology, because you wouldn't want to necessarily be driving manually and on a road that's so densely packed with vehicles. But the other great thing that it will hopefully do is provide greater access for those who can't drive, the elderly, disabled, children. It would provide a lot of freedom to a lot of people who don't have it. And then the third area is sustainability. There are some examples such as platooning, where we've been able to estimate the potential fuel savings, maybe 20%. There are other ways, though, that it will contribute to a sustainable, economy or society by eliminating traffic jams, reducing trip times, potentially in the future reducing ownership of vehicles, reducing the need for parking garages and parking spaces, and being able to convert some of those to other uses. So it's very exciting. The potential is very exciting. As I talk through sort of the historical part of this, I want to emphasize the different cycles of innovation that autonomous vehicles have gone through, but really that every technology must go through. It starts out with very exploratory and basic research and eventually works its way into commercial products, but it doesn't just happen once. It then repeats over and over again, but every time it goes through that cycle, it gets a little more advanced and a little bit more polished. And that's what we've seen really over the last 40 or 50 years. I want to introduce this little graphic that you'll see on the next few slides that indicates, sort of where the impetus and the funding for a particular project or program came from. And I'm including academic, inspired projects and non-military government, private industry, and then military. So, and that's what it will look like on the slides. So one of the earliest was a project that was done in the 50s in Nebraska, collaboration between the state of Nebraska and RCA. I just love the quote, "Driving will one day be foolproof and accidents unknown." So it took a while to get there, and we're still not there. But the promise certainly seems real today, and it probably seemed very science fiction back then. But that was a very future-looking experiment back then. Really in the 80s and 90s and going up till today, there are examples like Carnegie Mellon with their NavLab, which now has, it's in its 11th version for testing and developing autonomous vehicle technology. And NavLab, you could think of it as a platform upon which they've done several projects that fit onto that platform, like Ralph, which you know, in the mid-90s drove over 3,000 miles, and one trip from Pittsburgh to DC, 96% of that was steered autonomously. So the problem of, you know, following a road and following a lane has really been it was done a long time ago, and a lot of the effort, you know, since then has been dealing with edge cases, improving reliability. But this is an example that sometimes the challenge isn't the basic technology; it's other areas. So after that came along a government initiative for the automated highway. And this National Automated Highway System was a program that the DOT started also in the mid-90s. And, you know, it went strong for about 3 years and culminated in a demonstration in California of some autonomous driving. And one of the features that they emphasized was platooning. So this is an example of platooning, and with the benefits of fuel efficiency, of safety, of convenience. You can take your hands off the steering wheel, take your feet off the pedals, and just ride along. The difficulty with this that people became, you know, realized was that it was going to require enormous investments in infrastructure to deploy something like this. So really what happened was after that they changed focus a little bit and started to emphasize individual systems. For example, collision warning systems, lane departure systems. And this is really where a lot of these systems, you know, got their start, and we see them today in cars on the road. So this turned out to be a really good incubator for a lot of these technologies. Now, a little bit later in the mid-2000s, we started to have well-known DARPA Grand Challenge that seemed to capture the imagination of a lot of us. Did me, for sure. The first time, nobody won. In fact, I don't think anybody got over a few hundred feet. But they ultimately did have a winner in 2005, and then in the more difficult urban challenge, the Carnegie Mellon deal won. So going back to now a government initiative in the mid-2000s, the government started looking at connected vehicles, or back then it was called vehicle infrastructure integration. And it was around that time that the government had some frequency band reserved for them for DSRC networks, and that's been ongoing, you know, for 10 years. And recently, NHTSA announced its intention to enable this technology, and at some future date to begin to mandate and regulate it in light cars. So this is pretty exciting. There are several safety applications that have been identified, you know, that this could really help with, like forward collision, intersection movement assist. The great thing is that it's not limited to line of sight, but it can receive a message from a car that's 2 cars ahead, or maybe obscured by something. So this provides some benefits that I hope we'll see. And there's been a safety pilot going on up in Ann Arbor. Connected vehicles, people are also interested in the benefits of mobility and sustainability with connected vehicles. All right, something happened interesting around 2010, or at least that's when it sort of became public, that Google was working on a self-driving car. The Google self-driving car is direct lineage from the Stanford vehicle that won the DARPA Grand Challenge. Well, actually, personnel who worked on the Google self-driving car, I think, came from both Stanford and Carnegie Mellon. And I include this one because I believe it was really a disruptive moment for the industry. And it really got a lot of the other companies and the government thinking about this, starting to develop their own, to the point that now we see Mercedes and BMW and many other car companies planning for their own autonomous vehicles. Around 2012 is when NHTSA really got serious about looking at their autonomous vehicles, automated vehicles, and started to put together their automation program. And they're interested in things like the licensing, testing, regulating. The cybersecurity is a big concern for them. And what they did, one of the things they did was they wrote a letter recommending, laying all this out and recommending that for now, states would only legalize automated vehicles for testing purposes, research and testing purposes. So NHTSA feels, at least for the time being, that they're not ready for prime time, but they obviously see the promise and want to see the research continue. Now, NHTSA also has proposed their own taxonomy for levels of automation, and I have that shown here in a table. 0 through 4, where 0 is no automation, 4 is full driving. So the way this works is level 1 would be very specific functions like cruise control, active warning systems that will engage the brake or possibly the steering. When you get to level 2 is where you start combining these, and the driver can take their hands and their feet off the controls. But the driver is still going to be required to monitor the road, detect, keep track of all the different vehicles and signs and obstacles and objects. And they may need to take back manual control fairly quickly. It's not till you get to level 3 that you're really allowing the driver to disengage from the driving task and perhaps read a book, watch a movie, even take a nap. And that's kind of where I think the Google car is now, although their stated goal is full automation. And full automation, I'll talk about PRTs in a few slides. Other than that, we really don't have anything at level 4 right now. And then the last column is really a heuristic that's not part of the definition, but it helps you understand how much vigilance is required on part of the driver. In level 1, you need to be able to take control almost instantly. In level 2, you expect some fair warning, but you need to be vigilant and you need to be monitoring the automation. In level 3, you might be waking up from a nap and you will need some time to adjust before you can take control. So these are some good guidelines to help you understand those levels. And what's going to happen in the future, nobody knows for sure, but some of the vision might include things like very light vehicles, because in a crashless environment, we can start reducing the mass, and that begins what's called a virtuous cycle, where reducing the mass means that we can downsize the engine, we can reduce the fuel tank, we can make the drivetrain, brakes, and tires all smaller, and as a result, we can reduce the mass some more. So it becomes very beneficial. It might have impacts for car ownership in the future. where these autonomous vehicles act more like taxis rather than things that you own. And you can dial them up and they'll come pick you up and drop you off and then go pick up somebody else. So these things are obviously further out and depend on some good market penetration and possibly changes in the way that we design our cities and our roads. But, you know, they're out there, and it's kind of exciting. So that's my whirlwind tour of the field. I want to talk now about some of the state of the art, and there's two ways we can look at it. One is from a bottom-up approach of developing these, and the other is more of a top-down approach. The advanced driver assistance systems really represents a bottom-up approach in that they start as very narrow and specific systems, even back in the 90s as part of that NHTSA program. So this chart shows some of the systems that were commercialized since that time. This was done in 2011, and unfortunately it's horribly out of date already. Today's landscape looks a little bit more like this, where we have a lot more ADAS systems. We have a lot more complicated systems that are starting to get into level 2 automation. This figure is showing that graphically, and on the axes I have action and perception. So what that means is every autonomous agent, whether it be a robot or an automated car or a thermostat, really needs to do two things. It needs to perceive its environment, and it needs to act on its environment. Now, for a long time, cars have been getting better in the perception. We've been adding sensors. We're starting to add cameras and radar and ultrasonic, and now we're getting into LiDAR and GPS, and I'll talk about all the different sensor types later. But cars have been becoming able to perceive their environment much more, and as a result have become more capable of acting on their environment. Early example would be cruise control, but now we're getting into active warning systems and adaptive cruise control and lane keeping systems. And as we get higher in the levels, we're starting to combine those systems into more complicated ones like highway pilot or other combinations. And ultimately, an autonomous car will do almost all of the functions of the human driver. From the other end, we have a top-down approach, and it's interesting that level 4 automation has been with us for actually quite a long time. In these personal rapid transit vehicles, the earliest of which was in Morgantown, West Virginia, since 1975. And yes, there are compromises made, like they use guideways, they run at slower speeds, but they don't even have controls. So they're fully autonomous, and there's no operator in the cars at all. And so it's very interesting technology. And people are still working at the field from that end. There are several other examples. Masdar City is a very ambitious effort to create a highly technologically advanced city. Unfortunately, their PRT system is on hold due to some budget cuts, I think. But Europe has a program called City Mobile and City Mobile 2, of which the London Heathrow system is a part, and they have other systems that they're working on. And what's happening is these PRTs are evolving so that they're leaving the guideways, driving on plain sidewalks or roads, still at fairly low speeds. but they're starting to overcome some of the early criticisms of the technology. One was that they just wouldn't scale well because as you add more and more and more cars, you just have maintenance issues and repair issues. And but I think that things are moving in that direction, and ultimately we're going to see this top-down and bottom-up approaches meet in the middle somewhere. So let's get into a little bit of the technology that goes into these vehicles. This is a summary of some of the sensors. Very conspicuous on the Google car is that spinning LiDAR on top. And it gives you a 360-degree view of the environment around you. It was also the most expensive sensor, and still is one of the most expensive sensors. The Google car might, well, I heard it cost around maybe $150K, and the LiDAR that they used at that time was about half of that cost. But now LiDAR is in its third and fourth generation. The cost is coming down dramatically. And you have these inconspicuous LiDAR systems that don't have 360-degree field of view. They're narrower, but they fit, you know, on your bumper, on the side of the car, rather like the radar systems, and so they don't stick out so much. GPS and inertial measurement units have been on cars for a while. And it's a sensor that gives you a really good estimate of your location. Radar has also been used for a while, and people have different applications for which they use long-range radar and short-range radar. And there's a couple of different frequency bands that those operate at. But long-range radar can, you know, detect vehicles up to maybe 400 meters. And do things like adaptive cruise control. One of the interesting sensors that's being added is cameras because it gives you such a different view of the world than these others. And you can start to look at things like color and lighting and lines on the road and it gives you more cues with which you can begin to classify the objects that you see, that the car sees, as other cars or pedestrians or trucks or signs or what have you. Then DSRC is the sensor for connected vehicles, one of the sensor types for connected vehicles that does networking. And digital maps is something that people may not think of as a sensor, but it definitely is. It's simply a sensor where a lot of the computational effort has been done by somebody else at a previous time, and you're just accessing it. What do those sensors do for you? Well, they give you a view of the world. They answer the question, where am I in the world? And that problem is called localization. They also tell you where are other objects in the world with which I must interact, and that is the object detection problem. And a car that has multiple sensor types needs to be able to fuse all of that data together. It is a difficult problem, but the technology that people have used to do that has really enabled the development of autonomous vehicles over the last few years. There we go. And one of the keys to doing this has been the use of probabilistic methods, such as Bayesian reasoning, particle filters, Kalman filters, hidden Markov models, because the world is messy. There are uneven edges, lane lines are fading, you know, people are unpredictable, and so it's simply not possible to do hard thresholds that allow you to go one way or the other. So we work with probabilities, and it's been very effective for this field. Along those lines, I'm just going to put a quick plug in for some online courses if you're interested in learning more about that. I've taken both of these. One was offered at Stanford originally, but now is at Udacity. And they're both very interesting for learning about the technology of autonomous cars. Digital maps I've kind of already talked about. What happens when you don't have a digital map? Well, there are techniques to simultaneously create a map and then use the map to help you locate yourself. And that's simultaneous localization and mapping. Parking lots, there are lots of areas that you would need to use a strategy like that. And then there are algorithms that have been around for decades that are really well known, like A-star. And A-star has been developed and expanded and added onto a lot to deal with other, specific problems of pathfinding. So that's a fairly, well-developed area. One of the issues with maps is you must find the proper correspondence between the digital map and what your sensor is telling you. So GPS has a problem because you may be off by up to a meter. And that's important because it won't be able to tell you necessarily which lane you're in on the road. So the correspondence problem is an important one to solve. Let's talk about some of the challenges of automation. One of the primary ones is still weather. We don't yet know how we're going to, put an autonomous car on a road in the middle of winter in Minnesota, for instance. Snow and things that obscure the air and obscure the road are just still a big problem. Connected vehicle technology may be a savior in that you'll be able to communicate with the infrastructure. But this can obscure also sensors on your car. If you can't assume that everyone's going to clean their car off, right? So this is still a very challenging area. Another one is testing and certification of these devices. Testing and certification is a difficult problem. We have the NCAP program for some of these new collision warning systems that is able to educate and give consumers sort of a good picture of what they do and how well they work. You get your 5-star rating. But manufacturers have to test NCAP tests, NCAP, I think if that's what your question was. So let me give you an example of what I mean here. With some of these systems that we have today, you need to be able to test, and normally the manufacturer does this, for logic failures, sensor failures. They need to figure out how to reduce noise in their signals with Kalman filters. They need to be able to measure false positives, like their system detecting bridge abutments, and then stomping on the brakes. So these are all things that have to be overcome, and people have done a good job on overcoming them. But it does add to the testing time. Now, as we start going up the automation scale, we're starting to add more and more. We're adding all kinds of these probabilistic methods like particle filters. We're dealing with data fusion problems. We're dealing with enormous amounts of data from cameras and video. And so the number of test cases are starting to increase exponentially. I heard one auto manufacturer say that just for adaptive cruise control, they were able to identify about 3,000 distinct tests that they needed to cover. So it really gets crazy. Going up even further, you start to add in decision making and path planning, digital maps, all the range of speeds so that they'll work in parking lots and on highways, and it just explodes the number of test cases even more. So this challenge is going to be significant. before we see a lot of these vehicles on the road. One of the human factors issues that's being considered by NHTSA first, I mean, they even started tackling this, well, it was the first thing they started looking at in their automation program was transfer of control. And this answers a very fundamental question of how will the driver give control to the vehicle, how will the driver take control back from the vehicle. And let me just show you a little video here. And this is a very simple video. What it shows you is a car pulling onto a highway, pulling in behind a platoon, and then the automation will first take control of the pedal, the speed, and then as he settles in behind the platoon, the automation will take control of the steering. But what's not shown in this video is what would be the user interface that's required, you know, to inform the driver when they can give up control. How will this user interface prevent mode confusion? You know, how will this user interface help the driver take back control? Is it best to actually do it in a staged way where you do first pedals then steering, or is it best to do it all at once? I mean, these are all very fundamental questions that need to be addressed. Legality is another challenge of automated vehicles. There are some states who have paved the way with early laws, and generally we think that automated vehicles are legal in most cases, but a lot of things still need to be decided, such as liability. If you're not controlling the vehicle and you get in an accident, then should you be held responsible, or should the manufacturer be held responsible? And how much will that add to the price of the car? Security is another issue that's really important. It turns out, though, that security has always been somewhat of an issue. People have been able to hack into cars for a while, and they've demonstrated this. And there's many different, all of these things listed are different entry points that you can use to hack into a car. The issue is, before automation, there just wasn't a lot of motivation to do it, because what could you really do? And you could maybe spy on the person. You could maybe mess with their instruments a little bit. But now that we're adding automation into these vehicles, a hacker would be able to possibly take control of the brakes or run you off the road. So it's becoming more of a concern. And with connected vehicles, you know, people can do this remotely now if these concerns are not taken care of. As the vehicles get more complex, they start to add more and more networks internally. CAN bus has been a popular one, but there are things that are going to replace CAN bus that are even more data intensive and more computationally demanding. And so we need to worry about the security of all of these. Privacy is also a concern. The black boxes that some cars have and that will be required at some point on all vehicles are things that people can be concerned about, but can also help investigators to determine the cause of an accident and whether the automation was really at fault. The problem is that they record data that may be considered personal, or they will just record a lot of data. Network traffic, if it's identifiable, is a concern. Even if it's de-identified, there are ways to sort of associate data with one car or another by analyzing it. And as we start to add more and more data that's being collected, this concern gets greater. So the Google car, because it records video and LiDAR, is generating almost a gigabyte per second. Not that all of that is stored to disk, but it is generating. One of the strategies for dealing with privacy is a concept called privacy by design. And I think that the connected vehicles is a good example of a program that has taken these things into account from the very beginning. And they've designed, a network to be secure and have respect for user privacy. So I'm somewhat optimistic about the connected vehicles initiative. Now I want to make a couple of points that I sort of pulled from my research. I'm going to start with a little case study of an application called autonomous intersections. And I don't do it to pick on this application necessarily, but I want to look at it because I think it's the tip of a very large iceberg of considerations that we may not be thinking about and of unintended consequences. So there's a group at University of Texas at Austin who's been developing this for several years, and I think it's very exciting. It is a little bit further out in the future, but the idea is that you have an intersection that vehicles can communicate with and reserve their place to go through it. And when they do that, the timing can be managed such that you don't have to slow down or you don't have to stop. So no more traffic lights. And this can be engineered so it's completely safe, but if I put my human factors hat on, I have to ask how that will be perceived by the driver. So I'm going to show exactly the same scenario from the point of view of the driver going through. These are some of the scenarios, by the way, that my students were able to develop, and I call them automation scenarios. All right, did anybody flinch? That is somewhat disconcerting. One of the reasons that it's a problem is because people are not always good at estimating time to collision. When the time to collision is small, they're pretty good, but when it's 3 or 4 or 5 seconds out, people are not. They tend to underestimate it. And so because of that, as you're approaching the intersection, it's just impossible for you to determine if there's a gap there that you can shoot, right? So you really have to rely on the automation, and maybe it's better if you just close your eyes. So you really need to think about things like that. And there, as I said, that's the tip of a large iceberg, and there are issues along those lines that we need to think of even today as we're dealing with level 2 and level 3 vehicles. So speaking of levels, what's the trouble with levels? Well, we have this nice taxonomy. I'm going to be wrapping up here in just a second for questions. But we have this nice taxonomy that NHTSA has developed one, SAE has developed one. There are other examples of taxonomies for levels of automation that have been provided in the past. The problem with all of them is that, one problem is that they're not a roadmap for how this technology will be introduced or should be introduced into the market, right? They're just a definition of what the different levels are. Neither are these levels design guidelines. They don't necessarily help you at all design an effective driver-vehicle interface, or HMI. In fact, they might potentially discourage you from coming up with helpful ideas like adaptive automation strategies. Adaptive automation has been, put forward as one solution to the problem of drivers losing vigilance with automation. And so an adaptive automation strategy might jump from 1 to 2 to 3 to 4 and back again in order to keep the driver engaged and optimally, participating in the driving task. But you don't really get that from just looking at this. Let me give you another example of what I mean. The levels are clearly presented in terms of they follow the technological profile, right? The lowest technological challenge is no automation, and the technological challenges scale all the way up until fully autonomous. The problem with that is that people may interpret that as a roadmap, that we're going to go through level 1, level 2, level 3, level 4. If you look at it from a different perspective, like legal, you kind of see a different picture because from a legal perspective, it's really level 3 that's kind of the nightmare because you are allowing the person to disengage from the driving task, but still requiring them to take back control at some point. And so you have all these liability issues that come in. Let's put on a different hat and look at it from the human factors perspective. This is a problem that we're dealing with now, and NITS is well aware, which is why they're tackling human factors first. But at level 2, you are allowing the person to take their hands and their feet off the controls, but you're still requiring them to be absolutely vigilant and monitor the automation. And if there's anything that we know from automation research over the past couple of decades is that monitoring automation passively is not something that people are generally very good at. They become complacent. And so level 2 is probably the worst situation from the human factors perspective. So you kind of need to think about this holistically, and my fear is that we are actually going to really progress through these levels rather linearly, and we're going to have to deal with those human factors challenges and with those legal challenges. So this is my last slide. The future, we think, will be autonomous vehicles, but when will it come? Some people think 5 years, some people think 30 years or more. I would be interested, if you want to take an informal poll, if you could maybe type in what you think will be the number of years until we start seeing autonomous vehicles on the road in any significant numbers. So thank you very much for your attention. I would really look forward to hearing some of your questions.
Chris, one of the questions was, what about pedestrians and bicyclists? Would they need to wear a transponder to survive in this environment?
Okay, that's a great question. Well, that problem is being considered even from an ADAS perspective. So the new collision warning systems are beginning to look at pedestrians and smaller objects like that and do autonomous braking. And that's being done today with radar. The introduction of cameras is going to make that technology more robust and more, powerful, I would say, as it starts to classify the objects into pedestrians or bicyclists. And once it does that, if it knows that it's going to be a pedestrian, for instance, then it can begin to make some assumptions about the movement patterns of that object. It knows it's not going to move at 30 miles an hour, for instance. I think it's a challenge because the problem is you really can't afford to make any mistakes, can you? The first time that there is a incident between an autonomous vehicle and a pedestrian or a bicyclist, we don't really know what's going to come out of that. but I think that the technology is there, and it's going to get better to deal with those.
If anyone has any questions, please submit it on the chat forum.
How much participation? Yeah,
So
go ahead.
one of the questions. The question was, how much participation are you expecting a driver to get involved in, and how to determine the responsibility when an accident occurs?
Is this a question about liability in case there's an accident?
I would think so.
That's a really interesting question, and I will admit up front that I'm not an expert on the legal side of things. But from what I've read, from a legal framework, one of the issues is how autonomous vehicles will be treated. And one of the ideas about this is that you could think of autonomous vehicles a little bit more like elevators than you would something like trains. And that what that means for the legal framework of liability, I'm not entirely sure of. But I think it's safe to say that there will be some transfer of liability from the driver to the manufacturer. That's definitely going to happen. And I would hope that we'll be able to determine, through forensic analysis, exactly what was the cause of any particular accident. But yeah, I don't know exactly. It'll be interesting the first time that there is some kind of accident, exactly what's going to happen, because some people have said that it's going to be the end of the field, right? The first time there's a big accident involving an autonomous vehicle, then society will reject them, and that'll be the end. And I'm not that pessimistic about it, but I don't exactly know what's going to happen.
There was one question regarding does California or Nevada that have allowed Google car have had any problems in terms of crashes?
No, the Google car has not had any crashes. There have been, I think, a small handful of incidents, but I think that even those incidents happened while it was in manual control and not autonomous control. So I think they've been very successful at managing their research such that it's been fairly safe on the road. Actually, I had a chance to drive or ride in the Google car last summer on the highway out there, and did a great job.
The other question is there any pushback from the automakers since ownership would be less in this plan?
I haven't heard of any. The ownership issue is further out in the future, and I think that the concern of automakers right now is more one of being left behind. They want to get their offerings out there and be sure that they can begin to fill these niches and the demand that there might be for automation. Yeah, I think that they're probably looking at the ownership issue as something that they can try to shape themselves through their influence and through policy making. So I'm sure that they will have a hand. They'll they'll have an interest in the issue and they'll try to affect it as much as they can. But it hasn't been something that's been causing them to push against automation right now.
One question is, what do you think the role of federal government is in regulating and funding the development of this technology?
Yeah, great. It'll be significant, of course. NHTSA is taking a approach right now that is one of research, and they're not rushing into the regulation side of things, which I think is good, because there's a lot of innovation that has yet to be done by Google and by the other manufacturers. But clearly, there's going to be a tremendous need for regulation in the future. The issues that you see today with cars, like transfer of knowledge from one car to another, when these systems are so complicated and you get confused, right? That happens to all of us to some degree. And that's going to become worse as you have systems that are more complex, and they may distract you. You may not understand what they're doing, and you may just get into confusion about what mode you're in. I mean, mode confusion is one of the reasons we still have airline crashes today. So if that becomes a cause of car crashes in the future, it's a serious issue.
About the aviation industry, is there any lessons to be learned in terms of what they're doing in legal issues when a plane crashes on auto cruise or something?
Yeah, there certainly are, and the mode confusion issue I just referred to was one. I don't know exactly, what all will pull from aviation, because there are definitely differences between the two. The level of quality assurance and reliability that aviation needs to meet is much higher than what the auto industry needs to meet, and rightly so. But I think there are definitely lessons to be learned on the human factors front and on the reliability and security front.
There is one question regarding the rate of penetration of autonomous vehicles. What penetration rate would be a viable option for the whole system to work?
That's a good question. So the way things are going, we're introducing more and more of these collision warning systems, ADAS systems on the road, and so it's a little bit organic, and that will continue, I think. In terms of actually jumping to a much higher level of automation, I think the nice thing is you can put those cars on the road and they can drive in mixed traffic just fine. They have to be able to follow the rules of the road and interact with human drivers. Now, there are opportunities to do things like platooning, and for that, states and communities may be looking at managed lane applications. So we may start to see, express lanes or automated lanes. I think that's a possibility. But I think for the most part, I kind of see this happening gradually and organically. And I can't really say when we'll see significant market penetration. I mean, that's the $64,000 question right there.
One question is regarding, is there any industry-led effort to streamline the validation process for automated driving systems?
I'm sorry, could you repeat that question?
are there any industry-led efforts to streamline the validation process for automated driving systems?
I think that people are thinking about it a lot. When I was at the TRB summer workshop last summer, there were certainly a lot industry representatives there who were talking about the issue, like the example I brought up of all the test cases for ACC. And the technologies for dealing with things like that are ones that industry has been developing for some time, like model-based design and simulation-based test. And so I think that there is quite a bit of work on building out the test structure for the V model for verification and validation. But given the explosion of the number of test cases that you need to deal with, I think it is going to be a challenge to try to automate these tests and try to find ways to deal with just a larger quantity of data.
I think we have time for one last question. The question is, would the cars all go at the speed limit, or can they go over?
Or can they go over? Yeah. Yeah, I don't know. Yeah, I know. Maybe we should raise the speed limits a little bit. But certainly if they're in mixed traffic, drivers are going to be going above the speed limit. So should the autonomous vehicle go to the speed limit, or should it follow the traffic? On the one hand, I mean, what are the implications of an autonomous vehicle that doesn't follow the letter of the law? That's a serious issue. But on the other hand, if it's not following the flow of traffic adequately, then it'll become frustrating for the driver. So one of the things that Google saw in testing their car as they would come to an intersection is that it would wait its turn. And when it would wait its turn to go, it would never get to go because people would just go in front of it. So they had to actually build behaviors into the Google car to sort of inch out into traffic and sort of signal its intention to go, and then people would give it the right of way. So I think that's a really interesting question. I don't fully know the answer to it yet.
Thank you very much, Chris, for your time, and the presentation recording would also be posted online. So thank you all for attending this seminar series.
Thank you.